Hello everyone. So again, welcome back to the latest lecture session. As is our norm, I guess, let's have a quick recap of what we have been up to, right? So we have been discussing, let's say, groundwater remediation, or we have contaminated groundwater, and we are looking at the relevant aspects about, or what are the relevant options for you to be able to remediate that particular contaminated groundwater, right? So in that context, we looked at various options, primarily containment, let's say, and then I believe moved on to pump and treat, right? So in the context of pump and treat, obviously we dwell up, for a considerable period of time upon the relevant aspects, let's say, which would, let's say, determine the feasibility of the relevant pump and treat process. Yes. So in that context, let's try to summarize what are the relevant aspects, let's say, or which are the aspects that you need to consider, let's say, which can affect the feasibility of this pump and treat process considerably or even adversely, let's say, right? So the first aspect that we typically need to consider is the presence of NaPl, right? And then typically we also look at sorption of the relevant compound onto the organic fraction of the soil. Third, I believe we also looked at stranded source, let's say, again typically a feature when we have LNaPl, right? And I believe we looked at other cases too when we had different strata or stratification, let's say, right? So then the relevant hydraulic conductivities will be different for different strata out there, and thus obviously the contaminant transport is not going to be uniform, right? So let's just have a quick recap of these four aspects here. So NaPl, obviously non-aqueous phase liquid, right? It's non-aqueous, right? So again typically they are remarkably hydrophobic. So they can act as reservoirs for hydrophobic compounds, let's say, right? So let's say you have a hydrophobic compound and you have water here and you have NaPl here, right? So typically let's say the greater fraction of the relevant hydrophobic contaminant would want to stay in the non-aqueous phase liquid phase, right? NaPl, right? And again that's one particular aspect we looked at. So even if you pump out all the groundwater, let's say, right, you are still going to have a reservoir of the contaminant in the NaPl. So let's say you start out from here, let's say, groundwater concentration is in equilibrium with the concentration in the NaPl, let's say, and then let's say you remove this particular concentration or contaminant in the groundwater, right? But what happens now, again you are going to have equilibrium reached between these two phases of NaPl and the relevant groundwater, as in the contaminant is going to change phase from NaPl, or some of it from the NaPl phase into the groundwater, right? So again you are going to have issues with rebound. Yes, so that's one particular aspect we looked at. And similar context we looked at sorption as an adsorption of a hydrophobic compound, let's say, or hydrophobic contaminant, let's say, onto the organic fraction of the soil, or let's say if you have mineral oxides too there, right? So again what's the key aspect here? Hydrophobic compound, right? Again typically it would obviously not want to stay in the aqueous phase, let's say. So when you have organic fraction, let's say, or organic carbon present in the form of soil, let's say, or in the soil, pardon me, right? So obviously this particular compound would want to be adsorbed onto the relevant organic or the organic fraction of the soil, right? So moving on, then standard source. So here we have another aspect, as in let's say you have LNaPl, right? I think a simple figure would make this clearer, right? And let's say this is your groundwater table and this is your extraction well, and LNaPl typically light non-aqueous phase liquid, so it's unlike the DNaPl, it's not going to reach through or permeate through to the impermeable layer here, right? So let's say this is my LNaPl here, right? So if I start pumping, obviously I'm going to have a cone of depression, right? Let's say all the water in this particular zone has been pumped out, let's say, right? So after a certain time I would assume that, or I would observe that there is no further particular concentration of the contaminant detected in that particular water that's being pumped out. So then let's say I stop pumping, then what happens now? Again this groundwater table is going to probably come back to its original levels, right? And then again you have contact between the groundwater and LNaPl, right? So again now you have the system will try to reach equilibrium, as in the relevant compound will try to again enter change phase from NaPl into the groundwater, and again you are going to have contamination of the relevant groundwater here, right? So that's one particular aspect where we discussed, stranded source and stratification, let's say, as in I think the aspects or example that we looked at was that we have sand, clay, silty sand, or gravel, and so on. So the key aspect is, let's say I'm pumping water out, because all these different strata, let's say, have different hydraulic conductivities, as in the water can pass through some of these particular media relatively more easily compared to some of the other strata like clay, right? For example, I guess hydraulic conductivity remarkably greater in sand compared to clay, right? So if I keep pumping water out, or pump water out from that particular aquifer which has both sand and, let's say, clay, right? Obviously the water will move through easily through the sand, but not through the clay, right? So here, let's say, if any contaminant has diffused into the clay layer, that obviously will not be removed at the same rate as the contaminant that's going to be, or that was present in the sand layer, right? So that's one particular aspect, and I believe there are other minor aspects we discussed too, but due to lack of time I'm going to move on, right? So and then we started looking at, let's say, how do I estimate the time for remediation, right? So in that context, we did a simple mass balance, and we came up with a way to calculate the time for remediation as the total mass present, let's say, of that particular contaminant initially, by the rate at which you are removing or pumping out that particular contaminant, right? So I think simple mass balance, we arrived at this. So again, what is this about? The time for remediation and the pump and treat, it should typically be equal to the rate at which I am pumping, the total mass of the contaminant, right, divided by the rate at which I am pumping the mass of that contaminant out. So that's what I have here. So in that context, obviously we looked at 3 cases, or rather we need to look at 3 cases, some of which we already discussed. So case 1 is when we have the compound only in the aqueous phase, or it's only dissolved, let's say, right? Case 2, when you have the compound in the aqueous phase and also adsorbed onto the soil, let's say, and also adsorption, right? And case 3, right, when you have the compound in the aqueous phase, or it's dissolved, and you have adsorption, and you also have then NAPL, right? So I believe we discussed these 2 aspects, right? And I believe we need to look at some particular, we are going to look at a couple of examples in this context, and then move on to discussing 3, right? So before we go further though, let's just try to recap what we have discussed in this context. So the total mass of the contaminant in the case of let's say case 1 is going to be equal to porosity times the total volume, right? So this will give me an idea about the volume of the contaminated groundwater, right, times the concentration of the relevant compound, let's say, right. So it's what do you have here? The units of concentration are mass per volume of water or contaminated groundwater, right, and here I have porosity times total volume will be what is this now? Volume of contaminated groundwater, right. So I obviously end up with the mass of contaminant, right. So again, in this context, obviously time for remediation will be epsilon V C naught by Q C naught. So in that context, it's going to be epsilon V by Q, right. Obviously here we are assuming that C naught, or the the concentration doesn't change, right, as you start pumping out, but I mean that's minor assumption that we can make at this stage. So obviously as you see here, it's similar to the if I can call that the retention time here, let's say, right. So it's just the time required to pump out the total contaminated groundwater, but in which context though? Only in the context of if the compound is only present in the aqueous phase, right, in the aqueous phase, or is only present in the dissolved phase, right. So in this context, we moved on and discussed the relevant aspects with respect to case 2, when we looked at the compound being dissolved in the groundwater and also adsorbed onto the soil, right. So in this context, I believe obviously we are looked at the relevant aspects. So we are obviously going to have the mass of the contaminant that's in the groundwater. This is something we looked at in case 1, and then I believe we looked at the mass that's present in the or adsorbed onto the soil, right. For that, obviously I need the concentration of the relevant compound adsorbed onto the soil. So that's Q here, right. Q is typically, let's say, milligram of contaminant adsorbed per kg of, let's say, soil now, right. So adsorbed, and here in this context, for a linear, assuming a linear model, we and also looking at the partitioning coefficient, right. So again, the compound that's adsorbed onto the soil, let's say, or the ratio of the compound that's adsorbed onto the soil and the one in the dissolved phase, which is C naught here, they'll have there is going to be a relationship, right? Here I'm going to assume it's going to be linear, let's say, and here I'm considering the relevant coefficient to be the partitioning coefficient Kp, right? So, and obviously what else or how else do I need to modify that? I guess I have mass of contaminant per mass of soil, right? So, obviously I only want the total mass of contaminant adsorbed onto the soil, right? So, if I multiply this by density, the dry density, right, and density units, let us say mass of soil or dry mass of soil by total volume, right. So, to get my particular term here, I obviously need to multiply this by volume here, right. So, let us just try to simplify this further. Epsilon Vc naught plus Q, as I see here, it is Kp times C naught into rho B times V, density of the relevant or dry density of the relevant soil, total volume here, partitioning coefficient, let us say C naught is the concentration of the compound in water, and so on and so forth, right. So, one other aspect though, again, so what is this particular partitioning coefficient going to be dependent upon, right. So, here let us say what is the case now, I have let us say soil particle and I have compounds adsorbed onto, I guess star is not a good way to denote a particular compound, but let us go ahead and let us say this is my system, let us say, and I have this water out here. So, obviously I have let us say a fraction, let us say, or there is going to be equilibrium between the two phases. What are the two phases? The compound in the dissolved phase and the compound adsorbed onto the soil here, right. So, let us say if I remove this particular compound again, or both these two compounds in the dissolved phase by pumping the water out, what is going to happen now? Again I am going to have desorption of the relevant compound from the soil, and it will obviously change phase into the aqueous phase and again try to reach equilibrium, right. So, again there is going to be a particular equilibrium coefficient or such. So, again getting an idea about that is the variable that gives an idea about that particular aspect is the partitioning coefficient. But again, what does the partitioning coefficient itself depend upon? So, let us say if I have just silica, let us say will the particular hydrophobic compound be adsorbed onto silica? Not really, right. So, we are concerned with what do we say, the organic fraction of the relevant soil here, right. So, here again Kp would be dependent upon the soil partitioning coefficient, soil water partitioning coefficient times the fraction of organic carbon, right. So, this again is the soil water partitioning coefficient, and this is the fraction of organic carbon present. So, in this context obviously we assume that all the soil is made of organic carbon, let us say, and here obviously because not all the soil consists of only organic carbon, you need to plug in the relevant ratio of the relevant organic carbon fraction, right. So, in this context let us look at one particular example to understand, let us say, the relevant what do we say relative masses that would be present in the dissolved phase and the mass that would be present in the adsorbed phase, right. So, in this context I believe we also looked at the retardation factor, right, and how do we calculate that? That is going to be equal to the total mass by the mass in the dissolved phase, right. So, obviously that is going to be equal to epsilon Vc naught plus Kp C naught into rho B into V by epsilon Vc naught. So, end up with the retardation factor, R being the retardation factor, is equal to 1 plus Kp rho B by porosity, right. Again if I look at or try to understand what I have here, what do I have here? I have the total mass by the mass in the dissolved phase, right. So, what will this give me an idea about this as the retardation factor? It will give me an idea about the time, let us say, or extra time, let us say, required for pumping the total mass of the contaminant out, right. So, now let us move on and look at the relevant what do we say example. So, let us consider the partitioning coefficient, that is equal to soil water partitioning coefficient times FOC, right. So, for a particular example maybe let us consider PCE, let us say, industrial solvent and toxic to PCE. I believe the data we have are 209 liters per kg times, and now fraction of organic carbon present in the soil, I am going to assume it is going to be 1%, let us say. So, that is going to be equal to 0.01. So, I now end up with 2.09 liters per kg, right. I mean these are from the relevant EPA document, I guess, right, the KOC value. And now what is my R here, or retardation factor, was 1 plus Kp rho b by the porosity. So, obviously we need to have some what do we say, data regarding the density of the soil and the porosity. So, typical values, let us say I will take the typical values, porosity 0.4 and bulk density to be 1.6 kg per liter, right. So, now I am going to plug these values in. So, 1 plus 2.09 liters per kg into 1.6 kg per liter by the porosity is 0.4, and what do I end up with? Looks like I end up with, from what I have calculated previously, 1 plus 8.36, right. Again this is equal to 9.36 obviously. So, again what does this give you an idea about, right? It tells you that the mass of the relevant contaminant that is present in the dissolved phase, right, let us say if that is 1, the mass of the contaminant that is adsorbed onto the soil is 8.36, right. So, the ratio is 1:8.36, right. So, that gives you an idea about the relevant time required obviously to pump the water out. For example, if it was only in the dissolved phase, let us say, and if it took you 1 year, right, to pump the relevant contaminant out, pardon me, and now because of this retardation factor, which gives us an idea about the mass that is adsorbed onto the soil, let us say, right, if this were the scenario, you will see that it takes 9.36 years or 8.36 years more to be able to pump the relevant water out, right. As you see, so if the relevant compound is hydrophobic, as is the case for this particular PCE, let us say, the time required for what we say pumping out, obviously increases considerably, right. So, moving on to the relevant or next relevant aspect. So, here we are going to consider the case of the dissolved phase, right, and also the sorption or adsorbed phase, which is the soil adsorption, right, and also the NaPl case, right. So, let us try to come up with the relevant equation here. So, first the dissolved phase, we know that it is epsilon Vc naught, right, and adsorbed phase Q Kp into volume, not Kp, pardon me, rho b, right, plus the mass that is present in the NaPl phase, right. So, obviously here there is a minor correction that we need to look at, or need to incorporate here, as in where is the NaPl going to be present? It is going to be present in the pore space, right. So, here the pore space, and what is the pore volume here? It is epsilon V. So, obviously if you also have NaPl here, we are going to have to assume that part of the pore space is filled by NaPl and the part of the remaining part is going to be filled by groundwater here, right. So, in that case I am going to assume that S is the fraction of pore space, is the fraction of pore space, let us say, that is filled by NaPl, let us say, or occupied by NaPl, let us say, right. So, here how do I need to obviously change this particular term here? It has to be 1 minus S, right, as epsilon or porosity times volume earlier was the total volume of the contaminated groundwater, but here now it is 1 minus S times porosity into volume, because part of the pore space is filled by NaPl, right. So, here again what do I need? I need the fraction of or the volume of the NaPl. How do I get that? I know that is epsilon S epsilon into volume, right. So, this will give me an idea about the volume that is present in the particular what is this now? NaPl, right, a volume of the NaPl, right. So, here I have volume of NaPl, right, but obviously I am looking for the mass of the contaminant, right. So, here again I need to multiply that by the density of NaPl, right, and if NaPl itself is not the relevant contaminant, or if it is acting as what do we say reservoir for contaminant. So, as we know, it can be two cases, as in let us say the relevant compound can be the NaPl itself, or the relevant contaminant can be the NaPl itself, or NaPl or some other non-aqueous phase liquid can act as a reservoir or a phase onto which let us say the relevant contaminant is present in, let us say, right. So, obviously I am going to multiply that by X, let us say, X is going to be, let's say, the fraction that's present in, fraction of contaminant present in the relevant NaPl, right. So here let me again plug in a few values. So let's look at an example. But I guess before I go further again, I need to obviously again calculate, or to understand system better, let us try to calculate the retardation factor. So let's see what that is going to be here. So retardation factor is again going to be equal to m time equal to 0 by the mass present in the dissolved phase, so which is going to be this 1 minus S porosity V C naught, right. So that's going to be equal to 1 plus rho B, and Q is nothing but Kp times C naught. So Kp, right, by 1 minus S and porosity plus S times porosity times volume NaPl times mass fraction of contaminant present in NaPl by 1 minus S porosity V C naught. So what do I have here, or what can I cancel out? Epsilon V and epsilon V. So this is what this is my retardation factor, right. As we looked at the case earlier in the context of what is it now, just the adsorbed phase or the compound being adsorbed onto the soil, and also the compound being present in the dissolved phase. We looked at the relevant ratios, and we saw that it was for one part in what do we say, the dissolved phase, 8.36 parts in or adsorbed onto the soil, right. So let's try to look at a few typical values and try to calculate the relevant aspects. Okay. So I think I have a few values here. So let's try to look at some of the typical values. So let's say the pore space that's filled by NaPl, I'll consider that to be 0.1. Density of NaPl, I'll consider that to be 1.2 kg per liter. These are all typical values, not the hypothetical values, right. So concentration, I'm going to take initial concentration to be relatively less, 1 milligram per liter. And let's say I'm also going to consider that X, which is the mass fraction of the relevant contaminant in NaPl, to be 1, as in that it's pure NaPl, let's say, right. That's what I'm going to consider here. And let's try to look at the values that I calculated earlier. So looks like I end up with ratios of 1 plus a retardation factor equal to 1 plus 9.3 plus 1.33 into 10 power 5, right. So obviously the three values correspond to the three variables here, right. So what is this idea about? Obviously this is a reference, the mass in the dissolved phase, and this will give me an idea about the ratio of mass in the soil to the ratio of mass in the dissolved phase, and this will give me an idea about the ratio of mass in the NaPl to the mass in the dissolved phase, right. So if I look at that, I see that for one part dissolved, I have 9.3 parts adsorbed onto soil, and for this though I have, let's say, 133, right. So this is what I have here, so 1,33,000, right. And as you now see, let's say if you have NaPl, let's say your particular what do we say, pump and treat is going to be remarkably, or is going to be infeasible, right. So in this context, obviously even a minor volume of NaPl, let's say, that's present, well, throw your particular calculations or your particular feasibility of the relevant pump and treat into disarray, right. So here let's say, let me try to understand what the volume of what do we say, NaPl is. So here I have 1 minus S, and S I consider to be, or pardon me, S to be 0.1, 0.1 times porosity was 0.4 times volume, right. So 0.04, right, the volume, yes. So even if such at low volumes, let's say, as you can see 4%, let's say, right, we see that 4% of total volume is occupied by NaPl. We see that what is it, the retardation factor is remarkably high, let's say, and then the process feasibility obviously is pretty low. As in, what does this tell me now? That if it takes 1 year to pump out the water present in only the dissolved phase, let's say, but in this case where I have the dissolved, adsorbed and NaPl phases, it takes me more than a lakh or 1,50,000 years, or 1,34,000 years, I guess, or 1,33,000 years to be able to pump that out, right. So even if I, let's say, decrease some of the other values, let's say the volume of NaPl, let's say, that's present, or some of the other variables, you will still see that it's still remarkably infeasible, as in you don't want to keep pumping water out for tens or hundreds of years, right? So as you see, even if I take relatively more conservative estimates for the volume, or let's say the fraction of or mass fraction of the contaminant in the NaPl and such, you still see that it's going to be remarkably infeasible, right? So with these calculations or estimates, you should then be able to, what we say, or you would be better placed to be able to, let's say, check for the feasibility of the relevant pump and treat options, right? So considering these aspects though, typically again, what do we need to, what's the crucial aspect here? You need to be able to understand your particular aquifer, let's say, and also the site or contaminated site conditions pretty well, right? So if you do not do that, and you choose pump and treat, as you see, you can it can lead to failure, yes. So in this context, obviously you can do some trials in the laboratory and such, right? But those are different aspects which we are not going to go into here. But again, from looks like what people have observed, pump and treat widely used across the world, typically in the Western countries or Western world, right? So here, what transpired was that people who have tried to pump the water out and treat it, let's say, have underestimated the relevant complexities in the aquifer, and typically looks like most systems, they just stop their particular goal of remediating it, but only end up containing the relevant plume, right? So initially they started out with pumping the water out and trying to treat it, but again, because of these kinds of issues that they face, let's say, most people or most of the relevant or considerable, let's say, why use the term most, considerable number or fraction of the relevant people who chose pump and treat, they abandoned that particular goal, let's say, and then just try to limit their particular aspects to containing the relevant plume so that it does not spread to a wider area, right? So in this context, let's move on to the other aspect. So we have looked at, I believe, containment, right, and then moved on to pump and treat, let's say, and now we'll look at obviously the third case, a simple case where we are going to spend a little some time on it though, right? So obviously here, if let's say you detect the spill or release of the contaminant relatively early, right? So what can you do? You can look at source containment or source control, right? Source control, right? So obviously, how is this related to your particular case of groundwater? So typically you have the contaminated soil, and then let's say the groundwater then coming in contact with this contaminated soil, or the relevant contaminant flowing through that particular media and reaching the groundwater, right? So in that context, obviously, if it's an early release, what can you do now? You can obviously try to remediate that particular contaminated soil before, let's say, you end up with contamination of the groundwater. Again, contaminated soil, relatively limited area or extent of contamination, but once it reaches the groundwater, you see there are multiple issues out there. So obviously, you can look at source control, as in you can set up barriers, or relatively impermeable layers can be constructed, right? Or you can obviously, let's say, look at treatment of the soil or sediment, right? So here two aspects, as in you want to limit the transport of the contaminant or transport of the contaminant from the soil into the groundwater. That's one aspect that you can certainly look at. Or obviously you are going to look at treating the soil, right? But that's something we are going to discuss in the later parts of the course, right? So these aspects obviously, or you can obviously try to treat the soil to different ways. Again, these are aspects we are going to discuss later on in the during the later parts of the course, right? So now we are going to move on to the another particular treatment option, which is called a PRB, right? So PRB is a permeable reactive barrier, right? So just a couple of minutes about this particular option, and then we will end the session for today. So permeable reactive barrier is one of the most widely used techniques, again depending upon the type of contaminant and the aquifer and the depth of contamination, let's say. But again, there are numerous advantages to this particular process, maybe not widely or not adopted in India yet due to lack of maybe transfer of knowledge, let's say. Maybe the people, let's say the relevant people who are going to now learn about this can try to implement this and the relevant aspects that they face, right? So again, permeable reactive barrier, as the name indicates, is right. it's permeable, the barrier, you are going to put a barrier, but that's not an impermeable barrier, it's a permeable barrier, right? So in this context, you want to have the contaminated groundwater flow through this particular permeable barrier, and the key aspect is this particular barrier consists of reactive media, right? So you are going to put the relevant compounds that are going to either lead to degradation of the relevant contaminant in the groundwater, or let's say removal or changing phase from aqueous to adsorbed, right, in this particular case, right? So with that, I guess I'll end today's session, and we'll continue, or start discussing PRBs in greater detail from the next session, I guess, right? And thank you.